Hello, welcome to another module in this massive open online course. So, we are looking at example problems to understand the properties and applications of the Laplace transform. Let us continue our discussion. Okay, so we want to look at some other example problems for the Laplace transform. Okay. And what we have is basically we want to find, let us look at problem number 5. We want to find the inverse, correct? We want to find the inverse Laplace transform of xs equals the Laplace transform given by minus s square minus 2s plus 1 divided by s plus 2 times s plus 3 whole square, and the ROC is basically real part of s greater than minus 2, that is the ROC. Okay. And now remember, we can use this. So, this is now, if you look at this here, s plus 3 square, focus on this, this is a multiple pole. So, there is the poles are basically P1 equals minus 2, P2 equals minus 3, but this P2 equals minus 3, this is a multiple pole of order 2. Okay, this is a pole, this is a repeated pole, correct? This is a repeated pole of order 2. So, pole has multiplicity of order 2. Because you have the term of the form s plus 3 whole square, your multiplicity, pole with multiplicity equal to 2. Therefore, the partial fraction expansion will be of the form, you will have xs is equal to C1 by s plus 2 plus corresponding to s plus 3, you will have two terms, one is lambda 1 by s plus 3 plus lambda 2 divided by s plus 3 whole square. Now, the term, so multiplicity equals 2, which means the factor r is equal to 2. Okay. Now, C1, the constant C1 corresponding to s plus 2 in the partial fraction expansion, that can be found as seen before in the usual way, that is s plus 2 times s of s evaluated at the pole, that is s equal to minus 2, which is basically your turns out to be minus s square minus 2s plus 1 divided by s plus 3 whole square evaluated at s equal to minus 2, which is equal to minus 4 plus 4 plus 1 divided by 1, which is equal to 1. So, C1 is equal to 1, the coefficient C1 is equal to 1. Now, let us look at for lambdas. Now, to evaluate lambdas, we know we have the property that lambda r minus k equals 1 over k factorial, that is the coefficients corresponding to the repeated pole, that is s plus 3 whole square, pole minus 3, which has multiplicity 2. that can be evaluated. Lambda r minus k is 1 over k factorial dk s minus pi, that is the pole, ith pole, which has multiplicity r, s minus pi raised to the power of r xs over d s k, that is the kth derivative evaluated at s equals pi. Okay. Now, first let us set k equal to 0. Now, if k equal to 0, we have lambda r, and remember we have r equals 2. So, lambda 2 can be evaluated as 1 over 0 factorial times the kth derivative, k equals 0. So, there is no derivative, s minus pi, pi is minus 3. So, s plus 3 whole square into xs evaluated at s equal to minus 3. 0 factorial is 1. So, this is minus s square minus 2s plus 1 divided by s plus 2 evaluated at s equals minus 3, and that gives us, basically that gives us your minus 9 plus 6 plus 1 divided by 2 minus 3, that is minus 1, which is minus 7 minus 3 plus 2. So, that is minus 2 divided by minus 1, that is 2. So, lambda 2 equals, so we have the coefficient lambda 2 equals 2. Okay. So, this is the coefficient lambda 2. Now, if we set k equals 1, we have lambda 1, lambda r minus k, 2 minus 1 is 1 over k factorial, that is 1 over 1 factorial times d, the derivative, first order derivative of xs over, I am sorry, not xs, that is s plus 3 whole square times xs evaluated at s equal to minus 3. Now, let us look at d by ds of s plus 3 whole square times xs. Now, this quantity is basically the derivative of minus s square minus 2s plus 1 divided by s plus 2, which is basically equal to the derivative of, you can simplify this as minus s into s plus 2 plus 1 over s plus 2, which is the derivative of minus s plus 1 over s plus 2, which is equal to basically, now the derivative of minus s plus 1 over s plus 2, this is equal to minus 1 plus 1 over s plus 2 whole square. Now, therefore, we will have the derivative of s plus 3 whole square times xs evaluated at the pole s equal to minus 3. This will be minus 1 plus 1 over 2 minus 3. 2 minus 3 is minus 1 whole square, which is 1. I am sorry. So, minus 1, I am sorry, this will be minus 1 minus 1 over s plus 2. So, minus 1, which is equal to minus 2. So, basically what we have is lambda 2 equals, so I am sorry, lambda 1 equals minus 2. So, we have shown basically that we have evaluated the coefficient lambda 2 as 2, lambda 2 the coefficient corresponding to s plus 3 square is 2, and lambda 1 the coefficient corresponding to s plus 3 is minus 2. And therefore, the partial fraction expansion of xs can now be written as xs I hope you can see that xs can now be written as C1 over s plus 2, but C1 has been shown to be 1. So, 1 over s plus 2 1 over s plus 2 minus 2 over s plus 3 plus 2 over s plus 3 whole square. Okay. So, this is the partial fraction expansion of xs considering the pole minus 3 which has a multiplicity of 2. So, therefore, we have 2 terms, correct, pole multiplicity of 2, we have 2 terms in the partial fraction expansion. Since the pole P2 equals minus 3, as we have already seen, P2 equals minus 3 has multiplicity r equal to 2. Has the multiplicity r is equal to 2. Now, the ROC we have seen is real part of s greater than 2, which implies this is basically a right handed signal. So, implies xt x3 is basically a right handed signal. Okay. Now, 1 over s plus 2, the inverse Laplace transform for right handed signal is e raised to minus 2t ut, okay, 1 over s plus 2. So, we have the real part of s greater than minus 2, therefore, xt of t will be a right handed signal, alright. So, 1 over s plus 2, that has the inverse Laplace transform e raised to minus 2t ut. Similarly, 1 over s plus 3 will have the inverse Laplace transform e raised to minus 3t ut. Okay. So, 1 over s plus 3 will have the inverse Laplace transform e raised to minus 3t ut. Now, what about 1 over s plus 3 whole square? What is the inverse Laplace transform of this? Now, for the inverse Laplace transform of this, we will use the property that dxs over ds, dxs ds, that is derivative of xs, that is, let us write the complete property. If xt has Laplace transform xs, then dxs ds has the Laplace transform minus t xt. This is the property that we are going to use, and therefore, now you can see that 1 over s plus 3 whole square is nothing but minus the derivative of minus d over ds of 1 over s plus 3. Okay. And therefore, but we know what is the signal corresponding to xs equals s plus 3 basically has inverse Laplace transform. We have already seen that e raised to minus t 3t ut, which means 1 over s plus 3 whole square, which means basically this implies 1 over s plus 3 whole square, which is minus d over ds of 1 over s plus 3 will have inverse Laplace transform minus t times minus t, correct, 1 over s plus 3 whole square has inverse Laplace transform. This will have inverse Laplace transform. So, minus, yeah, so this will have inverse Laplace transform minus of minus t. So, minus this thing which is t times e raised to minus 3 t, t raised to minus. So, this will be, let me write it, minus of t times minus e raised to minus 3 t u t, which will be t e raised to minus 3 t u t. And therefore, finally, what will have, so 1 over s plus 3 whole square has the inverse Laplace transform t e raised to minus 3 t u t. And therefore, now we will put these three things together to find the inverse Laplace transform of the original signal. Remember, the original signal, the original Laplace transform, the partial fraction expansion is 1 over s plus 2 minus 2 over s plus 3 plus 2 over s plus 3 whole square. 1 over s plus 2 has the inverse Laplace transform e raised to minus 2 t u t. This has the inverse Laplace transform e raised to minus 3 t u t, and this has the inverse Laplace transform, well, this has the inverse Laplace transform t e raised to minus 3 t u t. So, therefore, the inverse Laplace transform of x s will be e raised to minus 2 t u t plus e raised to minus or minus 2 times e raised to minus 3 t u t plus 2 e raised to plus 2 t e raised to minus 3 t u t. Okay. So, that is basically the final answer that we. So, this is x t, which is the inverse Laplace transform of this is x t, which is the inverse Laplace transform of x s. Okay. So, this is the final solution, which is the inverse Laplace transform of the original, that is a Laplace transform that is given, which is x s, which is a rational function with a pole at s equal to minus 3 of multiplicity 2. Okay. All right. Let us look at another example. Which is inverse Laplace transform of the signal x s equals 3 plus 4 s e raised to minus s divided by s square plus 6 s plus 8. The ROC is real part of s greater than minus 2. So, this implies this is a right handed signal. Again, this implies once again this is a right handed signal. Okay. Now, we start by considering 1 over s square plus 6 s plus 8, this is equal to 1 over s plus 2 times s plus 4, which is equal to half 1 over s plus 2 minus half 1 over s plus 4. Now, remember for a right handed signal half 1 over s plus 2 is half, well, e raised to minus 2 t u t minus half 1 over s plus 4 corresponds to, has the inverse Laplace transform e raised to minus 4 t u t. So, this is the inverse Laplace transform, correct. This is the inverse Laplace transform of 1 over s square plus 6 s plus 8. Okay. Now, let us consider another term, let us consider s divided by s square plus 6 s plus 8, that is your s divided by s plus 2 times s plus 4, which is 2 divided by s plus 4 minus 1 divided by s plus 2, which has the inverse Laplace transform e raised to minus 4 t u t minus s plus 2 will be e raised to minus 2 t u t. Okay. But now, we remember we have this factor e raised to minus 2 s, remember we still have the factor e raised to minus 2 s, and to take care of that, to consider that, we will use the following property. Okay. We have e raised to minus, so let us say we have a signal, let us say we consider a signal u s, any signal u s, or let us say we consider any signal y s, which has Laplace transform, inverse Laplace transform y t, e raised to minus s t naught of y s has inverse Laplace transform y t minus t naught. Remember, we know this property, this is a delayed version of the signal. This is the delayed signal y t minus t naught, which implies, so this implies that e raised to minus 2 s y s has inverse Laplace transform y t minus 2. This implies 4 e raised to minus 2 s y s has inverse Laplace transform 4 y t minus 2. Therefore, now using this property we have 4 e raised to minus 2 s s divided by s square plus 6 s plus 8 has the inverse Laplace transform 4 times, well, the previously divided signal delayed by 2, that is e raised to minus 4 t minus 2 u t minus 2 minus e raised to minus 2 t minus 2 u t minus 2, which basically equals 8 e raised to minus 4 t minus 2 u t minus 2 minus 4 e raised to minus 2 t minus 2 u t minus 2. So, this corresponds to the second part. Therefore, the final inverse Laplace transform, that is the final inverse Laplace transform given corresponding to the original signal, that is you put these two things together. Remember, we have this, which is, let us say we call this one as result number let us say we call this as result number 2. We have our original result number or original result 1. Therefore, the final inverse Laplace transform net signal x t the net signal x t is given as, well, we have x s equals, remember x s equals, or let me just write x t, we have x t equals signal 1 solution in 1 plus 2, which is equal to, well, this is equal to, well, it is not exactly signal in 1, because the signal in 1 has to be multiplied by the factor of 3, because we are finding 1 over s square plus 6 s plus 8. So, 3 over s square plus 6 s plus 8 will be 3 over 2 minus 3 over 2. So, it will be now 1 plus 2, which will correspond to 3 over 2 e raised to minus 2 t u t minus 3 over 2 e raised to minus 4 t u t plus 8 e raised to minus 4 t minus 2 u t minus 2 minus 4 e raised to minus 2 t minus 2 u of u t minus 2, and this is your final solution. This is the final solution. Okay. So, basically what we have seen in this module is we have seen some slightly more advanced or challenging problems of evaluating the inverse Laplace transform. Alright. So, try to go through this again and understand the entire process. So, we will stop here and look at other aspects in the subsequent modules. Thank you very much.